So ML values represent you the orbitals in your subshell, basically which are similar in same in space and energy, but differ only with the three-dimensional arrangement. So if electron is doing kind of a clockwise rotation, if your electron is doing kind of a clockwise rotation, then the north pole will be appeared upwards. If the electron is doing some anti-clockwise rotation, the north pole will be appeared downwards. That is the opposite as the positive particle, right? So those are the ones which will be denoted by ms values. Spin created some mechanism with the use of that mechanism. These two electrons will be bound to each other, so that those won't repel. They are saying that don't put the second electron to that thing. Put the second electron to another orbital. That is the idea. Very clear, no? Right? If you are to put the second electron to same space, what will happen? Then some repulsions will happen. These guys, the chromium, molybdenum, silver and copper, those configurations can be stabilized if you are to release one electron from here to here. Last day we have started discussing about the quantum numbers, right? So there we have discussed about the first two quantum numbers, right? The principal quantum number, which actually gives us the idea of the main energy level where the electron occupies, right? And then we had discussed about the azimuthal quantum number, the L value, that actually gives us the idea of the subshell where the electron resides, where the electron occupies, right? So those are the two quantum numbers we have learned last day. Right now, we are going to learn about the other two quantum numbers in your four set of quantum numbers, right? The third quantum number, today we are going to start with that. That is the magnetic quantum number, which will be denoted in as a ML value, So that is our third quantum number, the ML value, right? We call it the magnetic quantum number. Right, magnetic quantum number. Right, that is our third one, the magnetic quantum number. Actually, when we are discussing about these quantum numbers, we are actually mainly focusing on 3 points. The first point is actually what this means, what this quantum number is representing us, right? What this means. And secondly, we are going to discuss about the physical idea, the picture about the quantum number. Thirdly, we are going to discuss about the restrictions with the quantum numbers, right? So those are 3 points mainly we are focusing on when discussing about the quantum numbers, right? The ML value, right? What this means? Basically, ML value means the directionality or the 3D arrangement of orbitals, right? The 3D arrangement of orbitals. So that is what represented by the ML value. So basically, when it comes to p subshell, right? When it comes to p subshell, we know we have 3 orbitals. In p subshell, we have 3 orbitals called as px, py, and pz. Right, the different orientations in 3D space, right? When it comes to d subshells, right? The d subshells are with 5 orbitals, like that. So those orbitals, their spatial arrangement is actually discussed with the ML value. That is the idea of the ML value, what it gives us, what information it gives us. Basically, the spatial arrangement of your orbitals in your subshell. That is what represented by the ML value, right? Secondly, right, what restrictions, right, are with this quantum number. Basically, we have some restrictions with the ML value as well, right? Not all the values are possible with the ml. Basically, it will be restricted by the L value. It will be restricted by the L value, right? We'll discuss about that thing as well, right? And the physical idea, basically physical idea is all about the three-dimensional arrangement, right? Okay, let's write the things one by one, just to complete note. Then while writing the stuff, we'll discuss more about this ml value, right? Okay, the first point. Just write the first point with the magnetic quantum number ml. Right, this is the first point, right? Another magnetic quantum, just write. Describes the come to red color and write orientation of the orbital in space. Orientation of the orbital in space. Orientation of the orbital in space. Right, that is the major idea with the ml, right? Describes the orientation of the orbital in space, right? Okay. Second point, the restriction, right? ml can have is a restriction. ml can have integer values from minus L to plus L, from minus L to plus L, including 0. Well, I'll explain that thing, right? This is a restriction. The ml values will be restricted by the L value, right? So basically for ml, right, you can't obtain all the values. The values are restricted so that minus L2 plus L along with 0, right? These are the capable values for ml, right? Just write this thing and then I'll do the explanation, right? Just write this one as well, right? Okay, so this is the idea. Integer values from L minus L to plus L. That is the second point, right? It's the restriction. Okay. We'll write the third one also, and I'll do the explanation. The third point with the ml, right? Just write. Number of possible values for ml denotes. Number of possible values for ml denotes. Number of possible values for ml denotes the number of possible values for ml denotes the. Come to the red color and write. Number of orbitals in the subshell. Number of orbitals in the subshell. Right? Number of possible values for ml denotes the, in red color, number of orbitals in the subshell. Number of orbitals in the subshell. Number of orbitals in the subshell. Right? Let's come up with the example. You can write the example as well. As an example. Right? As an example, just write. For P is equal to for P subshell. For P subshell. So when it comes to P subshell, you know the L value is equal to, Chris, any idea what is the L value for P subshells? Last day we have learned. Yes, any idea? For the S subshell, the L value is 0. For P subshells, the L value is 1. For D, it is 2, and for F, it is 3, right? So L value is 1 for P subshells, right? When it comes to P subshells, right? There are 3 possible. There are 3 possible. There are 3 possible ml values. Actually, there are 3 possible ml values. Are you with me? What are those ml values? The 3 possible ml values with the L is equal to 1. So ml is restricted by the L. So if the L is equal to 1, the available values for ml are minus L to plus L along with 0. That means minus 1 to plus 1 along with 0, the integers. -1 to +1 along with 0, the integers. So those are the available ML values. See, the available ML values are -1 to +1 along with 0. The available values are then -1, 0 and +1. So we are with 3 possible ML values for P subshells, right? Okay. So just write this thing as an example, right? Basically, as the point we had said that number of possible values for ML denotes the number of orbitals in the subshell. So you see, so you have 3 ML values with Lx equal to 1. That means you are with 3 orbitals in your P subshell. You are with 3 orbitals in your P subshell. That is what it means, right? 3 orbitals in your P subshell. P subshell, this ML represents gives you the idea of orbitals, right? You have 3 orbitals in your P subshell. That is what it means, right? Number of ML values available gives you the number of orbitals in the subshell, right? Okay. So you can write this stuff, right? Just write this thing. This means, right? This means you can write Lama, just continue. This means P subshell has this means P subshell has this means the P subshell has, come to your red color pen and write 3 orbitals which are similar in shape and energy. 3 orbitals which are similar in shape and energy. Write it in red color, right? This means P subshell has, come to red color and write 3 orbitals which are similar in shape and energy. 3 orbitals which are similar in shape and energy. Come to the normal color, but different in orientation in 3D space. So P subshell has 3 orbitals which are similar in shape and energy but different in orientation in space, right? So that is the idea. So such orbitals are called degenerate orbitals. What are degenerate orbitals? The degenerate orbitals are the orbitals which are same in shape and energy. Degenerate orbitals are the orbitals which are same in shape and energy but differs only in the 3D orientation, right? Those are called as degenerate orbitals. So just within brackets you can write in red color degenerate orbitals. In red color just write degenerate orbitals, right? Got the idea, no? Degenerate orbitals are the orbitals with same shape and energy but differs only with the 3D orientation in space, right? So the idea is this, right? So let's come up with the degenerate orbitals of P subshell. Right? It will be looks like this. So if you are thinking of P subshell, right? So we can come up with the 3 degenerate orbitals here. This is the Cartesian coordinate system, right? So I'll draw 3. Right. So P subshell is with 3 orbitals which are known as degenerate orbitals. That means those are with same shape and energy, right? But only the spatial arrangement. The relationship of the orbitals will change. See how those things looks like, right? Those are looks like this, right? So there is an orbital in P subshell along the x-axis, right? That is known as the px orbital. And another orbital is there in the P subshell which is actually along the y-axis. The same shape and same energy, only the direction to change. That is referred to as the py orbital. and then you will find another orbital in the p subshell, right, which is along the z axis. So it is referred to as the pz orbital. These three are the ones which will be denoted by ml values -1, 0 and +1. You can denote this as ml -1. This can be represented by ml 0 and this can be represented by ml +1. So ml values represent you the orbitals in your subshell. The orbitals in your subshell basically which are similar in same in space and energy, but differ only with the three-dimensional arrangement, right? That is what the ml values. That is what the idea the ml values represent, right? So Chris, you can write this stuff, right? So just draw these three orbitals which are appearing on x, y and z axes, right? So just complete the knot quickly. So I can send you a picture as well, right? Just try to complete while you are drawing the stuff, right? I'll take a picture and send it to you, right? So just draw the stuff, right? So three orbitals are possible with L equals 1. When it comes to L equals 1, the ml values possible are -1 to +1 along with 0. 3 possible ml values. That means you are with 3 degenerate orbitals with your L equals 1 subshell, p subshell. Right, no? Okay, we'll continue. So that is the idea. So keep it in mind, basically the ml values represent the degenerate orbitals. Got the idea on degenerate orbitals? Degenerate orbital means the orbitals with same shape and energy but differs only with the 3D space, right? So 3D arrangement. So these orbitals are with the same shape and same energy, differs only with the 3D arrangement, right, in space, right? So these are called as degenerate orbitals. The ml values, the -1, 0 and +1 represents the degenerate orbitals, right? Okay. So in the next page, right, you can write this one, the simplified idea about these things, right? So let's write it here. So I'll right, erase this stuff, right? To come up with the next picture. So I earlier said that you can't have all the values for ml. It is restricted by the L values. It is restricted by the L values. See, right, how it appears with the L values, right? So if you take the L value actually represents you the subshell, right? You can have ml values. Those represents you the degenerate orbitals. Right, and the number of ml values, that will give you the number of degenerate orbitals. Let's try to write copy this table, right? If you think of L equals 0 and L equals 1, L equals 2 and L equals 3, right? L equals 0 means, right, you are discussing about S subshell. L is equal to 1 means you are discussing about P subshell. That is what we have learned last day. L is equal to 2 means it is about D subshell. L is equal to 3 means it is the F subshell we are dealing with. Right? When it comes to these subshells, right? Let's discuss about the ML values possible. Not all the values are possible with the ML. So if the L is equal to 0, right? Minus 0 to plus 0 along with 0. Those are the ML values possible. Minus 0 to plus 0 along with 0. That is only 0. The only ML possible is 0. What about this? If the L is equal to 1, the ML values possible are minus 1 to plus 1 along with 0. If the L is equal to 1, minus 1 to plus 1 along with 0. Right? That means the ML values possible are minus 1, 0, plus 1. Always we are dealing with integers, right? No half values. No half values for first three content numbers. For the N value, for the L value, as well as for the ML value, you don't come up with the half values, right? Just the whole numbers, right? So when the L is equal to 2, the ML values possible are minus 2 to plus 2 along with 0, the integer values, right? The whole numbers. That means minus 2, minus 1, 0, plus 1 and plus 2. Those are the ML values possible. Let's come up with the L is equal to 3. If the L is equal to 3, right? L is equal to 3, we are supposed to come up with minus 3 to plus 3 along with 0, the integers, right? So that means always the whole numbers, right? Minus 3, minus 2, minus 1, then 0, plus 1 and plus 2 and plus 3. The values from minus L to plus L along with 0, the integer values, right? So you clearly see with L is equal to 0, only one ML value is appearing. With the L is equal to 1, 3 ML values are appearing. ML equals to 2, that means 5 ML values are appearing. And with the L is equal to 3, 7 ML values are appearing. Right? That means number of orbitals with the S subshell is 1, number of orbitals with the P subshell is 3, number of orbitals with the D subshell is 5, number of orbitals with the F subshell is 7, right? Number of ML values gives you the idea of the number of orbitals in your subshell, right? Number of orbitals with your F subshell is actually 7, right now? Number of orbitals in your subshell is actually 7, right now? So just complete this table, Aman, right? This is the summarized idea about the ML values, right? So ML gives us the some idea about the degenerate orbitals, and number of ML values gives us the idea of how many orbitals are available with your subshell, right? The number of ML values, right, gives you the idea of number of orbitals available with your subshell, right? So with S subshell only one orbital is available, with P 3 orbitals, with D 5 orbitals, and with L is 3, that F subshells 7 orbitals are available, right? So if you have to think of that idea, the idea is this, right? So if you have to take the fourth energy level, see, if you have to take the fourth energy level, right? Fourth energy level, right? You will have the L is equal to 0, L is equal to 1, L is equal to 2, and L is equal to 3, no? With the fourth energy level, right? You are with S subshells, P subshell, D subshell, and F subshell, no? These things is, right, with S subshells, right, you are having only one orbital. But when it comes to P subshell, 3 degenerate orbitals are there. 3 orbitals with same energy, this is the energy axis. 3 orbitals with same energy and the shape, but differs only with the orientation, right? When it comes to D subshell, you are with 5 degenerate orbitals. number of ml values represent the number of orbitals available with the subshell, right? With L is equal to 3, you are with 7 degenerate orbitals. If you are to denote the orbitals in a box like this, with a box like that, right? That is the idea, right? So if you are to mark the ml values here, you can mark them, right? This is ml equals 0. This is ml equals minus 1, 0 and plus 1. Here the ml values minus 2, minus 1, 0, plus 1 and plus 2. Here the ml values minus 3, minus 2, minus 1, 0, plus 1, right, and plus 2, and we need another one. 7 orbitals are available, no? So 7 is needed. Right? So this is the idea. Right? This is the idea, right? So this is what this is, right? So with S subshell only one orbital available, with C subshell you have 3 orbitals, with D 5 orbitals, and with F 7 orbitals. That is because of the number of ml values available because of this restriction, right? Okay, that is the total idea here, right? No? Are you okay with this, Namai? Are you got the idea? Did you get the idea here? That is all about the mls, right? Right now. Okay, those are about the ml values. Right. Let's come up with the next content number. So I wish you had written this stuff, right? Right. Let's discuss about the 4th content number then. If you are okay with this stuff, right? Let's come to the 4th content number. So far we had discussed about 3 content numbers: the n value, which gives you the main energy level, right? Main energy level of the electron occupation, right? So L value gives you the subshell. ml values gives you the degenerate orbitals, right? Number of orbitals with same energy and same shape, but differs only with the orientation. The ml values, degenerate orbitals, and the 4th content number now we have to, right? The 4th content number is referred to as the ms value. ms value, the spin content number. Let's discuss about that thing now, right? Okay. So you can have a screen capture as well, right? Quickly. So then we are able to continue. I'll send you guys the capture as well. Right now. Okay, let's continue. So we are up to the 4th content number now. We are up to the 4th content number, which is referred to as the spin content number. Let's discuss about the 4th content number now. Right, the ms value. The ms value. Spin content number. Right, before going to this section, do you have any problems with the things we have learned, Chris? Are you okay with the work? Yeah, no? No worries, no? Right, the 4th content number, spin content number. Right, actually the spin content number gives you kind of information which is referred to as the spin of the electron. It is like this. So electrons can spin clockwise or anti-clockwise. There are 2 possible spin types. when it comes to electrons, right? Two possible spin types. This is one thing, right? And this is the other thing. So I'll put it like this, right? This is clockwise and this is anti-clockwise. Two possible spin types, clockwise or anti-clockwise, right? Clockwise or anti-clockwise. So these are electrons, negatively charged particles. So those two spin types are represented by ms values. The clockwise spin is normally referred to as the plus half spin, and the anti-clockwise normally the minus half spin. That could exchange, right? Anyway, the plus half and minus half are represented, are given to two kinds of spins possible with the electrons, the plus half and the minus half. Let's discuss about a bit about these things, right? So basically, right, when a charged particle rotates, spins, right? So it will create a magnetic field. This quantum number is referred to as a spin magnetic quantum number. Spin quantum number or spin magnetism. This is referred to as a spin magnetism, MS, right? So basically, when a charged particle rotates, kind of a magnetic field will generate. So you have learned that, right, in your O levels, right? When a charge is going through, right, some magnetism will be generated. So I think with those nails covering with the copper wires, right? You may have done that thing. Do you remember, Chris? You may have done this thing, right? This kind of a nail covered with copper wires, right? And another nail covered with kind of another copper wire, right? Right? And charge is applied, right? You may have seen kind of magnetism. So let's come up with this thing as well. You may have seen some magnetism appearing. So this guy attract some pins, lighter spins. Did you remember that thing? When you have applied some current to this kind of copper wire in a nail, right? It will attract some nails, generating a magnetism there, right? So basically, when a charge is traveling, right? A charge is there, right? Movements in charge, right? So charge is like this now. When a charge is doing a circular motion, not a normal charge, right? It is kind of a circular motion, no? So kind of doing a circular motion, basically it will generate a magnetic field. When a charge is doing a circular motion, it will generate a magnetic field. That is what you have seen with your all stuff, right? So the same thing appears with these ones. So here also you have a charged particle which is rotating, kind of circular motion, right? Which is rotating, the charge is rotating. So what will happen? The point is you can come up with the direction of the magnetic field, the north pole and the south pole, with the use of screw rule of the remember that thing, screw rule can be used to come up with the direction of the magnetic field. So basically, if you are applying kind of these, right? If you are applying kind of these, right? This is the direction of the north pole. This is the direction of the north pole. That is what we have learned. No? If you are applying like this, it is the direction of the north pole here, right? So basically, when it comes to electrons, let's see, it's like this. No? So if you have a positive particle, if you are with a positive particle, right, where the clockwise rotation is happening, on a positive particle, so you can apply that thing clockwise on a positive particle like this, right? So clockwise on a positive particle, right? So that means you will create a magnetic field towards downward. Right? So north pole appearing at the bottom if the clockwise rotation is done right away on a positive particle. If kind of an anti-clockwise rotation is done on a positive particle, right? So like this, anti-clockwise rotation is done on a positive particle, the north pole will be appeared upwards. But we know the electrons are with oppositely charged. Electrons are negatively charged. That means, right, the directions will be the opposite. So if electron is doing kind of a clockwise rotation, if your electron is doing kind of a clockwise rotation, then the north pole will be appeared upwards. If the electron is doing some anti-clockwise rotation, the north pole will be appeared downwards. That is the opposite as the positive particle, right? So those are the ones which will be denoted by ms values. Which will be denoted by the ms values. Two opposite spins available with electrons. You don't have any other kind of spins, no? So if you can do two kinds of spins, clockwise or anti-clockwise. No other types are there, clockwise or anti-clockwise. Those are the two available spin types. So those are referred to as the ms plus half and the ms minus half. So if you refer this as the ms plus half, the other rotation is referred to as the ms minus half. Those actually gives you the ideas of two spins available with the electrons, right? This could be the clockwise spin, or then this could be the anti-clockwise. So quickly draw this stuff, right? Two opposite spins, right? Spin counter number, the two opposite spins. Clockwise spin and anti-clockwise spins will be denoted by ms plus half and ms minus half. So basically with quantum numbers, the only quantum number coming up with half values is actually the ms values, right? Only the ms values comes with half values. All the other three quantum numbers, the n, l and the ml, won't have any kind of half values, but only the ms carry some half values, right? Plus half and the minus half. Those are the two things available with the ms, right? No? Okay, right. So that's it with the ms. Just write this thing quickly about the ms, right? Under this, just write to complete the note. Just write this one. Put a point and light. Indicate the two opposite directions. Indicate the two opposite directions. Indicate the two opposite directions. The clockwise and anti-clockwise, right? Indicates the two opposite directions. Indicate the two opposite directions in which the electron can spin. In which the electron can spin. Indicates the two opposite directions in which the electron can spin. In which the electron can spin, right? And those are indicated by, just continue the statement number 1, and those are indicated by two values allowed for ms. Two values allowed for ms. Those are indicated by two values allowed for ms. And those are indicated by two values allowed for ms, put a comma, which are, write it in red color, ms equals plus half, and ms equals minus half. Ms equals plus half and ms equals minus half, right? Those are the only two possible ms values, right? Okay, that is all about the ms stuff. That is all about the ms values, right? All about the ms values, right? Okay, right. So we have studied about all the four quantum numbers now, right? N, L, ML and ms, right? This is about the ms, right? Okay, then at the page number 4, right? At the page number 3, you have some more points under the quantum numbers, right? You can go through that, right? Some few points are there, right? The restriction possible values for quantum numbers give rise to the following important observations. such points are there. So you can clearly go through that and see whether you could understand, right? Not hard stuff, right? Some restrictions will lead you to those rules, right? Such 4 rules are given there, right? Such 4 rules are given there. The first 3 are very straightforward. I'll go through that very quickly. The first one says the shell main energy level with the principal quantum number n consists of exactly n subshells. Yes, we know that. With the first energy level, only S subshell is available, one subshell. With the second energy level, you have 2 subshells, S and P. The third energy level, you have 3 subshells, SPD. With the fourth energy level, you have SPDF, 4 subshells. So n number of subshells are with the nth energy level. That is very clear, right? The second point, it says each subshell, each value consists of specific number of orbitals. Each subshell or each value consists of specific number of orbitals, means specific ml values. You know that, right? If we are discussing about the S subshell, it is with only one orbital, only one ml value. If you are with the P subshell, L equals 2, L is equal to 1, you are with 3 ml values. Always with P subshells, you have 3 ml values, 3 degenerate orbitals. Always with D subshells, L is equal to, you are with 5 ml values, -2 to +2, along with 0, the 5 integer values, right? So they are with D subshell, you are with 5 orbitals. So with any subshell, they are with kind of specific values as number of orbitals, right? That is what it says. With the third point, that is also clear, and we have came across those points with the earlier discussions, right? So, but the fourth one, that is our major discussion here, the fourth point, it says like this. The fourth point, it says in your note, it is there, no need to write this one, right? It says, in an orbital, maximum of 2 electrons can be there and they should be of opposite spins. In an orbital, maximum of 2 electrons can be there and they should be with opposite spins. That is another kind of a restriction available with the MS, because with the MS you are with only 2 values. So in an orbital, if you are to reside 2 electrons, right, those should be with opposite spins. That is what it says. So if kind of orbital comes up with 2 electrons, those should be with opposite spins, right? Plus half and the minus half, right? That says you can't have the spins like this. So you can't have the spins like this, sorry. This is not available. That is what it says, right? In an orbital, if the 2 electrons are there, right, those should be with opposite spins. That is what it says, right? In an orbital, maximum of 2 electrons can be there and they should be of opposite spins, right? So this discussion will be further carried on with the next topic, right? We will discuss this thing further with the Pauli's exclusive principle, and I'll give you the reasons for this thing as well. Up to that moment, right? For this moment, right? Just skip this one, and with some few minutes, we'll discuss more about this point, right? Why we need to have kind of opposite spins if the 2 electrons are in your orbital, right? We'll discuss that thing, the reasons with some time, right? Okay. So first of all, let's do some exercise. Chris, let's do some exercise with what we have learned, right? We have learned, covered the total things about the quantum numbers. Let's come up with a simple exercise here, right? So let's see whether we have totally understood these concepts of quantum numbers. See, so it is like this, right? Let's consider some matter. So that is also at next page, your next page, right? Let's consider the chlorine atom. So chlorine is 17th atom. Chlorine is 17th atom, right? Chlorine is 17th atom, which is with 287 configuration. According to your O-level stuff, chlorine is with 287 configuration. So basically, in energy levels, according to the new theory, new cloud model, orbital concepts, right? Those 70 electrons are occupy these kind of subshells, right? And the energy levels. So when it comes first energy level, when it comes first energy level, n is equal to 1, right? N is equal to 1. You are with only s subshells. When it comes to n equals 2, you are with s subshells as well as p subshells. The second energy level contains s and p subshells. In p subshell we have 3 orbitals. When it comes to third energy level, you are with s subshell, right? P subshell, with 3 orbitals, as well as d subshell, right? Occupy 17 electrons. S and P subshells are enough for the third energy level, right? So this is our energy level diagram according to new atomic model, cloud model, right? So let's discuss about the electronic arrangement of fluorine, right? Basically the electrons are arranged like this. In an one orbital you can have only 2 electrons, right? So we have to come up with 17 electrons altogether with the chlorine. So those will occupy their orbital like this, right? Finally we had said no, only 2 electrons are available in an orbital, right? So this is the idea. So let's discuss about the quantum number sets of these things, how to write the quantum number sets, right? So I'll write this thing, right? If you are to refer this one, I'll label some atoms, right? So to copy the idea, I'll label some atoms, right? So I'll label this one as A, this as B, your C, right? D, E, and the atom F here, sorry, electron F, and G and H. I have labeled some electrons. Sorry, I have some other stuff as well. No? I'll put the H there, right? So now I am trying to come up with the set of quantum numbers for these labeled electrons, right? So these labeled electrons, I am trying to come up with the set of quantum numbers, right? First of all, I'll write the set of quantum numbers for one electron, right? Let's see. First, I'll write the quantum number set for this one, this electron. Let's try to come up with the quantum number set for this one, right? Set of quantum numbers contains 4 numbers: n value, L value, ml value, and the ms value, right? Let's try to come up with the 4 quantum numbers for this one. The idea is this, right? Okay, let's come up with the quantum number set. Yes, this electron is in second energy level. This electron is in second energy level. So the first quantum number, n, denotes the energy level of your electron. N denotes these numbers are like this: n, L, ml, and ms, right? Those are the 4 values, right? N, the first quantum number n gives you the main energy level you are with. That is the second energy level, right? So this electron belongs to second energy level. So the n value is 2. N value is 2, right? What about the L value? L value gives us the subshell. L value gives us subshell. It is about the P subshell. P subshell means L is equal to 1. L is equal to 1. What are L values? The subshells. Remember no? L value. So if you are with, right, if you are with S subshell, the L value is 0. P subshell, the L value is 1. D subshell, the L value is 2. F subshell, the L value is 4. So 3, sorry. So that means, right, as you are with the P subshell, your L value of this electron is 1. right now. What about the ml values? What are the ml values? So if you are to refer the ml values with these ones, I come with a different color, right? So if you are to think of the ml values with this one, so we can put it as like this: the ml available values. So for L is equal to 1, for the L is equal to 1, the available ml values are what? -1 to +1 along with 0. That means available ml values are these guys. Available ml values are these guys, right? For L is equal to 1, -L to +L along with 0. Today what we have learned, the restrictions with the ml, right? So we can denote the ml values here. ml equals -1, 0, +1, right? Those are the three orbitals, degenerate orbitals represented by the ml values. So in this case, this electron occupies the ml equals 0 orbital. This electron occupies the ml equals 0 orbital. So ml value with this orbital is 0. ml value with this orbital is 0. Right? ml value with that orbital is 0. Right? What about the ms value? What about the ms value? When it comes to ms value, this electron is a downward electron, right? If you take the upward electrons as ms is equal to +12, we can take the downward electron as the ms equals -12, right? ms equals -12. So that we can say this downward electron is there. We are referring to that thing. That means ms value will be -12. So this is the quantum number set for this electron. This is the quantum number set for this electron, right? So I'll give you some time, Chris. Can you come up with the quantum number set for other electrons as well? Can you come up with the quantum number set for other electrons as well? Or do I need to do another example? Or can you complete the stuff with other electrons? Chris? Do I need to come up with another example? Yes, I'll do another one, right? Right? Just try to come up with the values for your spaces, right? In your spaces, right? So I'll do with another one, right? So few values are available here. No? So let's come up with A, B, C, D, E, F, no? Right? And we have G and H as well. Right? Let's come up with first these things, E and F. Right? The A means A. This A electron is at the first energy level. N value means the energy level. It is at the first energy level. The first quantum number is 1. It is at the S subshell. S subshell means L value is equal to 0. L value is equal to 0. Right? Then if the L value is 0, ML will be always 0. ML will be always 0. Right? For L values, L value 0, -0 to +0 along with 0. The only capable value for ML is 0. So ML value capable for L value 0 is just 0. Right? So ML 0 is there. Right? And the final thing, that is actually the A electron is the upward electron, the upward spin. That means ms plus half. That is the first one. That is the A, the quantum set for A. Right now, Chris, did you receive the tutes? I wonder whether you received tutes. Lastly, it was a POE day, no? Right? Thought we have sent the theories, right? Just see. If not, probably you will receive them tomorrow. Right. Okay. So this is how we are to assign the quantum number set for a given electron, right? So what about the B? Let's do this stuff quickly. For B, so the B electron is at the first energy level. So the energy level is 1, the n value is 1. It is at the S subshell. The B electron is also at the S subshell. S subshell means the L value is 0. If the L value is 0, always the ML value possible is 0, right? And the B electron is downwards, right? That means it is the minus half. Downwards means the minus half, right? No? Let's come up with other stuff as well. The C1. So C electron is at the second energy level. C electron, this one at the second energy level. So principal quantum number is 2. N value is 2. And it is at the P subshell. P subshell means the L value is 1. Right? It is at the ML equals minus 1 orbital. Right? So ML value is minus 1. And you see, that is a kind of upward arrow. That means the upward spin, let's denote it as plus half. Like that, you can complete the set of quantum numbers for D, E, F, and G and H. Right? I'll write the answers here, so you can correct them. Right? Check them and correct if you have written it wrong. Right? Anyway, the D. See, the D at the second energy level, N value is 2, and the P subshell, L value is 1, that means, right? And D electron is at the ML is equal to 0. We have 3 degenerate orbitals now. ML is minus 1, 0, and plus 1 with the P subshells, right? So 0, and this one is kind of upward arrow, that means plus half. Right now, the D value. What about E? Again, second energy level, P subshell. So second energy level, P subshell. So ML value is plus half, the plus 1 orbital, where the electron resides, right? And it is again an upward electron, so that is plus half for MS. Right now? What about F? Let's copy the F value as well. F electron. It is at the second energy level, P subshell, the second energy level. N is 2, P subshell, L is 1. Then it is at the ML equals minus 1 orbital. So it is minus 1. The F electron, right? It's a downward spin, right? So downward spin means minus half. Kind of anti-clockwise spin, right? That is the idea, right? What about the G and H? See, the G and H. The G electron. See, G electron. Third energy level, P subshell. The N is equal to 3, the third energy level, P subshell means again L is equal to 1. Third energy level, P subshell, right? So again we can denote these orbitals as with some ML values. So ML values available with L is equal to 1 is minus L to plus L along with 0. That means minus 1, 0 plus 1. The ML is available, right? So we can write those values. So with the G electron, it resides at the ML equals minus 1 orbital. It means minus 1 orbital. And it's a upward electron. Upward electron means plus half. Upward spins for the G electron. Right now? Let's come up with H as well. Third energy level, P subshell. Third energy level P subshell. Third energy level means n is equal to 3. P subshell. P subshell means L is equal to 1. P subshell is L is equal to 1. And that is at the ML0 orbital. So let's put it as 0. And then it's a downward, it's a kind of a downward electron. So it could be -12. That is how, right, we are supposed to write the quantum number set of a given electron, right? No? So do you have any issues, Chris? Are you okay with this stuff? Right, no? Okay, no worries, no? Right. So Chris, did you got your results? All your results? What happened? It is okay, no? Very okay. Sorry? Sorry?
I can continue the class. Results are enough for that.
Results are enough to continue the class. Okay. So you better study hard now then, right? These are not easy stuff, no? Right. Maths and science are okay, then you can continue. Right.
From meta to beta now, sir.
Sorry?
I had improved from meta to beta.
Meta to meta.
Meta to beta.
Meta to vada. Okay. That's better. So you have to do more work to this now, right? So it's not like O levels, right? So anyway, results, actually all results are not important, right? If you are trying hard and do this stuff day to day working is to be done, then you can do this stuff easily, right? So what you need to do is actually you have to study, day to day studying should be done. That is the case, right? So if you can do that, right, basically you can come up with better results with the A levels, right? Even I have heard some people even with 3 A's at the O levels got some 3 A's with the A levels as well. Out of 9 subjects, some people were there. Out of 9 subjects, just got only 3 A's, 3 A passes, or some such kind of child was there, right? And ultimately he came up with 3 A's. So that things are possible in A levels, right? If you are studying hard with a good purpose, good goal, yes, you can excel this one, right? So try hard, right? Okay. So you have more time as well right now. These days you are with holidays, right? So schools is start, right? With no time. So anyway, just study hard. All the 3 subjects should be followed, right? I mean, don't do only one subject, right? You have to love all the 3 subjects, right? So then do them properly, and you will be able to get some good results. Okay. Anyway, this is all about the quantum numbers, right? So, right. So now we know how to come up with the quantum number set if they have labeled some electron, right? If a labeled electron is given, we now know how to come up with the set of quantum numbers for that electron, right? Okay, that's it. Let's come up with the next point, next section, right? They are actually we are going to discuss about 2 theories, which is also with some connections with the quantum numbers, right? The first principle or the first theory is referred to as the Pauli's exclusion principle, right? Pauli's exclusion principle, right? Let's discuss about that thing, right? After this one, let's go to the Pauli's exclusion principle, right? Okay, right. Pauli's exclusion principle. See what it says. Right. Pauli's exclusion principle. Pauli exclusion principle. Right. Let's discuss about this stuff. First of all, let's write the definition here, please. Right. After that, we can discuss what it says. Right. Okay. Let's write the definition here. So the given space, you can write the definition. Right. Let's write that one. Right. In red color, you can just write this one. Just write. No two electrons in an atom, within inverted commas, just write in red color. No two electrons in an atom, no two electrons in an atom can have the same set of 4 quantum numbers. No two electrons in an atom can have the same set of 4 quantum numbers N, L, Ml and Ms. No two electrons in an atom, no two electrons in an atom can have the same set of 4 quantum numbers N, L, Ml and Ms. Right? That is, yeah, you can close the inverted commas. That is actually what Pauli's exclusive principle says, right? No two electrons in an atom can have the same set of 4 quantum numbers N, L, Ml and Ms, right? So that is Pauli's exclusive principle, right? Right. In the next line, just write. In the next line, just write with the normal color. The normal color, you can write. Further, this indicates that. 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 Just continue, Lamai. I'll explain the thing, right? I'll explain the thing after writing the stuff, right? Further, this indicates that. Further, this indicates that. Come to the red color and write. Come to the red color and write. An orbital can hold a. An orbital can hold a. An orbital can hold a maximum of 2 electrons. An orbital can hold a maximum of 2 electrons. An orbital can hold a maximum of 2 electrons. And they must have opposite spins. And they must have opposite spins. An orbital can hold a maximum of 2 electrons and they must have opposite spins. And they must have opposite spins. Right? Let's discuss about that idea, right? An orbital can hold a maximum of 2 electrons and they must have opposite spins. Let's discuss what it says, right? Okay. The idea is this, Lamai. So we know about the orbitals now. Basically, we denote them with these boxes now in individual diagrams of atoms. We can denote the orbitals as boxes, right? Yes, orbitals are with different shapes, right? Spherical things, double, dumbbell stuff are there. But in individual diagrams, we can use these boxes, right, to denote orbitals, right? So the Pauli's exclusion principle says, right, in an orbital, you can have maximum of 2 electrons, right? So it is that an orbital can hold a maximum of 2 electrons. An orbital can hold a maximum of 2 electrons, and Pauli's exclusion principle says those 2 electrons should be like this with antiparallel spins. With antiparallel spins, right? And they should have, and they must have opposite spins, right? That is the idea. An orbital can occupy only 2 electrons and they must have opposite spins. This is what it says. This is the Pauli's exclusion principle, right? So it could be like this or like this. If you have with 2 electrons in your orbital, those should have opposite spins, right? Up, down or down, up, both are okay because this is plus half, this is minus half, plus half, minus half. 2 opposite spins are operating, right? These are acceptable. These are acceptable according to Pauli's exclusive principle. Acceptable. Right? So, and these kind of computations are not accepted by the Pauli's principle. This or this. These things are not accepted according to Pauli's principle, and you clearly see the reason is, even if you are with 2 electrons, those are with same spin. Those are with same spin. So those are not accepted. Not accepted. Not accepted. Right? So this is the idea of Pauli's principle, right? So orbital can have maximum of 2 electrons, and those 2 electrons should be with the opposite spins. Right? You can't have these kind of conformations when regarding electrons in an orbital. Right? That is the Pauli's principle. That is very clear, Lamai. That is very clear. See, what will be the reason? Let's discuss a bit about the reason of the Pauli's principle. This is about the reason of the Pauli's principle. What could be the reason? Right? This reason. Why is that? So basically, orbital means what? Orbital means what? Orbital means the maximum probable space where you can find your electron. The maximum probable space where you can find your electron. That is what an orbital means. Right? Maximum probable space where you can find your electron. Right? So, if you are with 2 electrons with that space, with that maximum probable space, right, with that small space, right, if you are with 2 electrons, let's say you are with 2 electrons, if you are with 2 electrons with that space, like this, if you have 2 electrons with that space, this is orbital, let's say one is orbital. With this small space, you are with 2 electrons. So what will happen? The electrons are negatively charged. So that those will repel from each other. Because the electrons are negatively charged, so that those will repel from each other. So those conformations are available. So it could be like this. Even the 2 electrons could be like this, right? So that those will repel from each other, and basically if these repulsions occur heavily, right, those will eject from the orbital, right? So we should come up with a method, we should think of a method to put these electrons together. We should come up with a method to, we could think of a method to put these two things together. Right? Actually, that is what done by the 2 spins, 2 available spins. See? So, when the 2 electrons are with opposite spins, right, like this. When the 2 electrons are with opposite spins, right? So, 2 electrons are with opposite spins. One carries the north pole here, the other carries the north pole here. When 2 electrons are with opposite spins, north pole here means south pole here. So what will happen? Right? When the 2 electrons are carrying some kind of opposite spins, right? Kind of opposite spins, sorry, not the case, right? And this one is there, so the other one will carry some kind of opposite spin, right? South pole here, north pole here, south. Yeah. When two electrons are carrying some opposite spins, what will happen? So those will attract. With the use of spin magnetism, with the use of magnetism created by the spin, right? Spin created some magnetism. With the use of that magnetism, these two electrons will be bound to each other, so that those won't repel. Yes, there are some repulsions are there, but these things will be bound to each other heavily with this magnetism present with the rotations of those charged particles, right? So that is what it says. To occupy two electrons in your orbital, to occupy two same sign charge particles in some single space, those should be bound by an even greater force, right? That will be provided by the magnetism created by the spins of those electrons. So those spins should be antiparallel. Without such, you can't think of having those two electrons closer to each other in a one single space, as those are with the same charge. The repulsions will occur. So you have to overcome those repulsions and get attracted. For that, spin magnetism is used, right? So that is what Pauli's exclusion principle is. If you are to have two electrons in your single orbital, those two electrons should have two opposite spins. Right now, that is a simple idea of the Pauli's exclusion principle, right? So it says, I think it is clear. Do you have any problem, any inquiry about this thing, Chris? Right? Are you clear with the idea of the Pauli's exclusion principle? Right. No? Okay, and that is the idea. So, so you can write these two things, this picture as well as this one. You can come up with these two pictures, right? So actually, these two electrons are bound with the magnetic field created by the things. Two things are bound with the magnetic field created by the spin of electrons, bound by created by spin of electrons, right? That is the idea of the Pauli's exclusion principle, right now? Okay, that is the idea. And under that, with the same space, you can write under this, you can write like this. Some another example, right? So when it comes to the electronic arrangement of lithium, right? Electronic arrangement of lithium. When it comes to the electronic arrangement of lithium, it will be like this. It will be like your 1s orbital is with 2 electrons and your 2s orbital is with the other electron. This is the electronic arrangement of lithium level, right? This is the accepted electronic arrangement of lithium, right? This O, this, both are accepted electronic arrangement of lithium. even this. These are accepted electronic arrangements of lithium, right? These are accepted arrangements, right? This is some example, another example for the existence of Pauli's exclusion principle, right? But you can't have the lithium like this, like this. So you can't have all the 3 electrons. You can't have all the 3 electrons in lithium in single orbital like this. You can't have all the 3 electrons in lithium in a single orbital like this. Why is that? Because these conformations violate the Pauli's exclusion principle. These conformations violate the Pauli's exclusion principle. You see, these 2 are with the same spin. These 2 are with the same spin. Here also these 2 are with the same spin. If the spin is same, right, that is not a good thing. That is not a good thing to have, because if the spin is same, that means the magnetic field is also the same, right? So that will also comes up with the repulsions. So these 2 can't be bound together. These 2 can't be bound together, and even these 2 can't be bound together to occupy the same single space, the orbital. So that these are not accepted. These are not accepted. So that when it comes to the lithium atom, definitely you need the 2s, the second another orbital to come up with the third electron. So you can't have 3 electrons in one single orbital, because it violates the Pauli's exclusion principle. It violates this effect, right? So these 2 can't be there at the same orbital, even these 2, because those will repel from each other and then will be ejected from the orbital. So that definitely, right, you should come up with another orbital to occupy the third electron. The third electron can't be occupied at the same orbital. That is the idea, right? So with lithium also, this Pauli's exclusion principle is so confirmed with the lithium's electronic arrangement. So you can come up with this thing as well, right? So these 2 conformations are accepted for lithium, but not the other 2. But not the other 2. So just quickly write this thing as well. Right. This is all about the Pauli's exclusion principle, and that is also some principle appearing with the 4th quantum number. With the use of 4th quantum number, we can basically describe or explain this principle, Pauli's exclusion principle. Right now. Okay. Right. Are you okay, Chris? Do you need more time to write this one? It's okay, no? Yeah, you can take a screen capture as well to complete the note. Right, okay. So that is all about the Pauli's exclusion principle. After this, we'll discuss about the Hund's rule as well. Hund's rule, another principle which will be very important when discussing about the arrangement of electrons in an atom, right? Hund's rule. Let's discuss about that rule as well, the Hund's rule, right? Hund's rule. right? Right, Hund's rule actually not have much to do with the quantum numbers. Anyway, let's discuss about that thing. The Hund's rule, right? First of all, just write the rule. Let's write the rule, and then we'll discuss about the idea, right? Then we'll discuss about the idea, right? Hund's rule. Just write the rule, right? The Hund's rule states that 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 put a comma and write it in red color with the next line. With the next line, you can count the next line and write it in red color. You can continue with the red color, right? Like this. For degenerate orbitals, within brackets, orbitals with same energy, close the brackets, put a comma. The lowest energy is attained when the number of electrons having the same spin is maximized. Again, I am telling you, for degenerate orbitals with same energy, the lowest energy is attained when the number of electrons having the same spin is maximized. Right? Okay, that is the Hund's rule. Right? At the next line, just write this thing as well. After completing note, we'll discuss the point, right? At the next line, you can come to the normal color and write. This means that put a comma. When filling electrons to degenerate orbitals, within brackets, sub energy levels, close the brackets, put a comma, sub energy levels, close the brackets and put a comma. And in the next line, just write it in red color. Come to the next line and write it in red color. Electrons occupy orbitals singly. Electrons occupy orbitals singly. Single, that is single. Electrons occupy orbitals singly to the maximum extent. Electrons occupy orbitals singly to the maximum extent. Electrons occupy orbitals singly to the maximum extent possible with same spin. Electrons occupy orbitals singly to the maximum extent possible with same spin, magnetic quantum number. Again, I am telling you, electrons occupy orbitals singly to the maximum extent possible with same spin magnetic quantum number. Within brackets, right? Parallel spins. Close the brackets. Okay, I'll explain you what it says. It is like this, Laman. It is like this. Right? Let's take an example. This is what Hund's rule says, right? Right? Copy the example. Right? If you are thinking of, right? If you are thinking of 3 electrons appearing with the p subshell, right? If you are thinking of, let's see, your nth energy level p subshell, let's say you are with 3 electrons. Your nth energy level p subshell, you are with 3 electrons. If this kind of a electronic configuration is there, Hund's rule says right, when writing the three electrons here, when writing the 3 electrons with the p subshell, you know the p subshell is with 3 p orbitals, right? P subshell is with 3 p orbitals. M indicates -1, 0 and plus 1, right? Anyway, so when arranging 3 electrons to these orbitals, Hund's rule says you have to occupy orbitals singly to the maximum, singly to the maximum, singly to the maximum with parallel spins, singly to the maximum with parallel spins. So like this, or like this, singly to the maximum with parallel spins. One electron each with each orbital, singly to the maximum. And all should be with same spin, with parallel spins with same spin. So this is what is accepted. These are the conformations accepted with 3 electrons residing with the p subshell. Let's discuss about the situations which are violating this rule. So if the things appearing like this, if you locate the electrons like this, if you are locating the electrons like this, 1, 2, 3, this is actually violating the Hund's rule. This is violating the Hund's rule. This is violating the Hund's rule. Why is that? Why is that? What is the reason here? You are not occupying the electrons singly to the maximum. So first electron should be occupied singly until you complete all the subshells. Until you complete all the orbitals, you have to put 1 electron each to all the orbitals first. But here the third electron is here. That is not good. This is not violating the Hund's rule, right? See, another violation kind. So if you had put some like this is also violating the Hund's rule. This is also violating the Hund's rule. Singly to the maximum, that is okay, but with parallel spins. But with parallel spins, out. Anti-parallel. This is out. Right? That is out. So basically, this conformation is out because of this. Right? Because of that. So we need parallel spins. Parallel spins. Parallel spins. Parallel spin is needed. Because of that, this is not accepted. And this is not accepted as you are not occupying the orbitals singly to the maximum. It's because of this. Because of that, we can't accept this one, right? So the problem here is, right, singly to the maximum. So electron should be added to all the orbitals before you coupling, before you write in the antiparallel spins, right? Singly to the maximum needed, right? Because of these things not accepted. Not accepted. These are the reasons. Right? So let's come up with another example. Let's come up with another example. Kind of D stuff. ND 6 or something.
These rules are not relevant for the quantum number writing, no? These are different principles, no?
Yeah, these are different principles. But this is related to quantum numbers like this. This is actually related to quantum numbers in a very simple manner. It's like this. So, with the Hund's, yes, Chris, any?
Yeah, but the quantum number we have already done the spin up and down.
Yeah.
Plus or minus half. That is quantum number when the examiner asked us to the quantum number, we had used that previous rules, no? Not these new rules, but they are learning now. No? One rule and the other one. No? We are not using these rules. We don't allocate the electron to that email, no, sir?
So basically, Chris, right? When we are allocating electrons to an atom, when we are referring electrons to an atom, basically we need to come across these rules as well, right? The thing is, the Pauli-Sexton principle should be followed, right? Pauli-Sexton principle should be followed. That means if you are allocating 2 electrons to one single orbital, if you are allocating 2 electrons to one single orbital, definitely Pauli-Sexton principle should be followed. The idea is that the 2 electrons should have the 2 different spins, right? With the ms values, the 2 ms values of the electrons should differ, right? When you are to put 2 electrons to a orbital. So that is how the Pauli-Sexton principle relates to the quantum numbers, right? So Pauli-Sexton principle says you should have 2 opposite spins. That means you should have 2 different ms values with the 2 electrons you are trying to occupy in one single orbital. That is how that thing relates to the Pauli-Sexton principle relates to the quantum numbers. And when it comes,
Based on that only we wrote the answers, no? Based on that only we wrote that numbers, no? What we wrote earlier, electron allocation. Based on that only, based on the power suit only, we wrote that electron allocation. But this is because this is exceptional, no? This is different one because here we can allocate one electron to the one
yeah, I'll explain the stuff, right? So yeah, the kind is this. So basically, when we are thinking of putting electrons to atoms, right? So actually, when we are thinking of putting electrons to atom, we have to discuss allocating those electrons with 3 steps, right? The first thing is we should concern how the electrons are arranged in a one single orbital. How the electrons are arranged in one single orbital. That will be discussed with the Pauli-Sexton principle. How the electrons are arranged in one single orbital, right? Those two should be antiparallel. That is what discussed in the Pauli-Sexton principle, right? But here with Hund's rule, what we are actually discussing is how the electrons should be arranged with a subshell. How the electrons should be arranged, right, in a subshell. That is what Hund's rule says, right? This is actually referring to how the electrons should be arranged in a subshell. Subshell means orbitals with same energy. Orbitals with same energy or degenerate orbitals. Right, so that is the idea. So I'll explain further, right, to get the clear idea. It's like this, no, Chris, if you want to think of the total atom here, right, like n is equal to 1, n is equal to 2, such things are there, no? So we have orbitals as well, no? Like this. This is the S subshell and P subshell, the orbitals are there. So basically, Pauli's exclusive principle, Pauli, the one we learned early, right, is about, right, putting electrons to one orbital, like this, right, putting electrons to one orbital. Those should be antiparallel. That is Pauli's exclusive principle, right? Now we are referring to Hund's rule that says how we are supposed to allocate electrons to one single subshell. Earlier, electrons to one single orbital. Now, to one single subshell. That is what Hund's rule says. It says if you are to allocate electrons to one single subshell, that means degenerate orbitals, one single subshell, it says you have to allocate electrons like this. One here, two should be here, not here. Two should be here. The third electron should be here. You can't couple the electrons until you occupy one single electron each to all the orbitals available in your subshell. In your subshell, first you have to occupy one single electron to all the orbitals with these parallel spins. Then only, this is first electron, this is second electron, this is third electron, then only fourth electron can be coupled. That is what the Hund's rule says. Hund's rule is all about filling electrons to a subshell. Earlier, the Pauli's exclusive principle is all about filling electrons to a one single orbital. Right? When you are filling the fourth electron here, the Pauli's exclusive principle also comes to play. When you are filling the fourth electron here, not only the Hund's rule, but also the Pauli's exclusive principle also should be considered. That is why we need to put the fourth electron downwards rather than going for upwards. Right? Because then we are dealing with one single orbital. With one single orbital, the second electron should be filled according to the antiparallel spin situation. So the Hund's rule says the electron should be filled singly to the maximum, and then you can couple. That is all about filling electrons to a one single subshell. Are you clear? Still do you have the problem? Clear, no? Yes. Again I am telling you, Pauli's exclusive principle is all about filling electrons to one single orbital, one single square. Those should be antiparallel. Hund's rule is all about filling electrons to more than one orbital. Filling electrons to more than one orbital with same energy. Filling electrons to more than one orbital with same energy. Those are referred to as degenerate orbitals. So those are the orbitals and at a one single subshell. So Hund's rule is all about filling electrons to a subshell. So when we are supposed to fill those electrons, first you should fill parallelly one electron to each of the subshells. After filling one electron each to all the subshells, all the orbitals, then only you can come up with the parallel spins. That is Hund's rule. Right. So let's discuss about this conformation again. If you are to fill electrons to kind of a D subshell, D subshell comes with 5 D orbitals. D subshell comes with 5 D orbitals, right? So we have to fill 6 electrons here. So it should be like this: 1, 2, 3, 4, 5. First of all, you have to fill 1 electron each to all the orbitals available with your subshell. Right? This is the first electron, second electron, third electron, fourth electron, fifth electron. After filling 1 electron each to all the orbitals available in your subshell, then only you can couple with the antiparallel spins. This is 6th electron. This is the acceptable electronic structure when you have 6 electrons in a d subshell. So one can have like this as well. These are also acceptable. As a d subshell, you are with 5 d orbitals. You can come with like this as well, no? Downwards 1, 2, 3, 4, 5. No worries, no? Still the same spin, no? Parallel spins, no? Then you can couple. Then you can couple even in here. So the electrons 1, 2, 3, 4, 5. This is the 6th electron. No worries. This is also accepted. Right? So first you fill 1 electron each singly to the maximum until you come up with the 5th electron. After that, the 6th electron is added to any of the orbitals, but there you have to couple that with the antiparallel spin, because they are the earlier rule, Pauli's principle applies. When you are coupling the electrons, when you are putting the second electron to a one single orbital, you need to come up with the antiparallel spins. Right now? Yeah. The 6. Yes, no need to say put the 6th electron here. You can come up with anyone. No worries. Right? Okay. That is the idea. So that is all what. If you need another one, I'll write another one. Right? See, these are few confirmations. So you can start filling the electrons from here actually. 1, 2, no worries, sir. 3. Anyway, those should be parallel spins, right? Until 5 electrons, those should be parallel spins. Until you fill 1 electron each to all the orbitals, those should be parallel. Then you can come with some 6. Anywhere else, even here. Right? So those are accepted. Those are accepted according to the Hund's rule. That's all about filling electrons to orbitals with the same energy. Orbitals with the same energy. Those are referred to as degenerate orbitals. Accepted. Right? That is the idea. So I'll write some false confirmations as well. You can't write like this. These are some false confirmations. You are not supposed to come up with these, right? 6 electrons can't be added like this. This is false. This is false. Right? You can't couple. You can't couple. You can't couple until you come up with 1 electron each with all the orbitals available. Right? You can't couple until one electron is added to all the degenerate orbitals. You can't couple until 1 electron is added to all the degenerate orbitals. So they're not accepted. Not accepted. So you can't write that. You can't write that, right? So those are the false confirmations, right? First you have to write 1 electron each to all the orbitals available with the subshell, and those should be with some parallel spins. Then only you can couple antiparallelly. That is the simple idea. So you can have this, write these terms. So I'll send you a picture as well, right? You can have a screen capture as well. Oh, yeah, we'll send you a picture. Okay, then I'll give you example how the electrons are filled, right? See, let's come up with, I'll come up with the same atom, chlorine, right? I'll do the same thing with the chlorine, how the electrons are filled to that chlorine, the 17 electrons, right? Okay, see, do you have this idea properly? So, okay, we'll go with the chlorine again. Is chlorine, right? Chlorine atom, which is 17 neutrons, that 287 thing, right? This is a chlorine atom. Let's see, this N equals 1. You have the N equals 2. And you have the N equals 3. At the N equals 1, you have just S subshell. You have here S subshell as well as P subshell. P subshell is with 3 degenerate orbitals. And in case 2 is with S subshell as well as P subshell as well as D subshell also. But yeah, we'll write the D if you need, right? Right? But no need of adding electrons to D when we are referring to the chlorine, right? Chlorine is your 17th atom, 287. Let's try to fill the electrons there. Yeah, I'll tell you, right? The first electron, right? Normally, Chris, the electrons are filled to atoms to attain the lowest energy. To attain the lowest energy, the electrons are filled, right? Because lesser the energy with you, right? It says you are stable, right? Stable. What it means by the stable? Do you have any idea about the stability? Yeah, Sorry.
You will jump out.
No.
You will jump out and instead with sodium or something.
So no, it's like this. So I feel what is meant by stability. So stability means, that is just the definition of stability. Stability means if something is something is there, not changing for a longer time, right? If something is there without a change for a longer time, we can say such a thing is stable. No change for a longer time period, right? No change happening with a great time period, we say such a thing is stable, right? So stability can be achieved easily when you are with less energy. Yeah, when you are with great energy, you are jumping here and there and you are running, and yeah, you won't stay at a one place for a longer time. So you are always changing when you are with great energy. When you are with more energy, you are running here and there, and you will change quickly with no time. But if you are with no more energy, if you are with very less energy or no more energy, you stand still. You won't run anywhere else. So that you stand still. You will be as it is for a longer time, right? So you are stable, right? So stability is that, right? Staying for a longer time without a change. That is stable, right? So basically stability can be achieved even with atoms when the energy is low, right? So atoms get stabilized when their energies are low. That means basically when filling electrons, the electrons are first filled to the lowest energy levels. Electrons are first filled to the lowest energy levels, right? Because to achieve the greater stability. That is also referred to as the Aufbau principle. That will be discussed with the next point, right? With the next theory, we will discuss with the Aufbau principle. Anyway, according to that, so electrons will be filled from down to upwards, right? Okay, so let's discuss about the two rules we have learned, right? First thing is actually the Pauli's exclusion principle. Yes, Pauli's exclusion principle says this. Yes, the first electron is filled here, is normal. The Pauli's exclusion principle says the second electron should be filled actually to the same atom, same orbital, but it should be with the anti-parallel spin. Should be with the anti-parallel spin. That is Pauli's principle. You put the second electron according to the Pauli's exclusion principle. The second electron is anti-parallel, right? So in an orbital, the electrons are filled. In an orbital, the electrons are filled according to the Pauli's exclusion principle. Third electron, yes, you can fill the third electron here. Third electron, third. The fourth electron, it should be here. Fourth electron should be with anti-parallel fin. Is first, second, third, fourth. When you fill in the fourth electron to the same orbital, it should be the anti-parallel spin. That is also about the Pauli's exclusion principle. Pauli's exclusion principle, right? Okay. Fifth electron, it will be filled here. The fifth electron. Coming up with the sixth electron now. Coming up with the sixth electron should be done here. Should be done here with parallel spins rather than coming up with here. Rather than coming up with here, the sixth electron should be filled here. That is what it means by the Hund's rule. Hund's rule. Hund's rule says you can't put the sixth electron here. You can't put like this. You have to put the sixth electron here. Because when it comes to filling electrons to degenerate orbitals, when it comes to filling electrons to subshell, orbitals in the same subshell, you have to fill electron one by one to each of the orbitals available parallelly. Then only you can put the next stuff anti-parallel. First you have to come up with one electron each, maximum, singly to the maximum with parallel spins. That is what Hund's rule says. So actually, Chris, this is also a simple idea. This is not a very unthinkable idea. This is also a simple idea. I'll tell you why. See, it's like this, no, Chris. The idea is this, no. Let's think of these things. Let's think. This is the px orbital. This is the py orbital. Let's think this is the pz orbital. Let's try to picturize this one. If you need to get the clear idea of this situation, right? So we have three orbitals. One is on the z axis, one is on the x axis, and one is on the y axis. These are three orbitals available, na? Right? This is your atom and three orbitals available now. This is pz, py, px. Right? The idea is this. The idea is this. So, if the first electron is added here, they are saying that don't put the second electron to that thing. Put the second electron to another orbital. That is the idea. Very clear, no? Right? If you are to put the second electron to same space, what will happen? Then some repulsions will happen. Rather than putting the second electron to the same orbital, it is better to put the second electron to a different space. So these two won't get repel from each other. They are saying to put the third electron to the other one. Rather than putting the third electron to the same orbital, just put the third electron to another orbital. That is what it says, the seventh electron. Very simple idea. If you are to put the sixth electron here like this, what will happen? The repulsions will occur, and yes, that will be minimized by the Pauli's exclusive principle, that effect. But still some kind of repulsions will occur, no? Still some kind of instability will be there with the atom, no? So that is why they are saying just put the sixth electron to here. So no any kind of repulsions then. So that is better to resize electrons. Put the seventh into other orbital. One electron each. Singly to the maximum. After that you can couple this stuff. Eighth one here. Here we can put the 8 here as well. Area here, both are same, right? Same orbital, right? 9th, 10th. That is the idea. This is about the Hund's rule. Filling electrons to one single subshell. Degenerate orbitals. Are you okay with that idea, Chris? Then 11th electron here, the 12th here. That is about all about the Pauli's principle. 13th, 14th here according to Hund's rule. 15th here according to Hund's rule. 16th here according to Hund's rule as well as Pauli's principle. 16th here according to Hund's rule as well as Pauli's principle. So you are adding the second electron to the orbital. That means that should follow the Pauli's principle, the antiparallel spins. And the 17th electron here according to the Pauli's principle as well as Hund's rule. Right now? Are you okay with the idea? That is how we are supposed to fill the electrons to an atom, right? Okay, so it is very important to follow the Pauli's principle, which is actually giving you the idea of filling the electrons to one single orbital, and we need to follow the Hund's rule as well, which gives you the idea of filling electrons to one single subshell, some degenerate orbitals, right? Okay, right, that is about the Hund's rule. Let's come up with the ultimate one of ultimate rule of filling the electrons, that is referred to as the Aufbau principle. That comes up with the electronic configuration. Electronic configuration. This is a very important part, Chris, right? So electronic configuration, this thing will be appeared in all the lessons, even in A levels and all the stuff, right? This will be always there, right? Even with the unit 2, unit 3, even all the units, basically this section is there. Electronic configuration is very important part, right? So let's try to come up with the electronic configuration. You may have written this thing in your O levels, the 288 configuration. That is electronic configuration, right? Actually, so but in O levels you had used the Bose theory to come up with the electronic configuration. The energy levels, the electrons with the energy levels. With the first energy level, you can have up to 2 electrons. With the second energy level, you can have up to 8 electrons. With the third, 8 electrons. So by considering the energy levels, you have written the electronic configuration in your O levels. 288 configuration is about those, right? That is actually referring to the Bose model. But nowadays, we are referring to the cloud model. That is our modern atomic theory, cloud model. And with the cloud model, we know not only the energy levels, but also the sub-energy levels. The subshells, the sub-energy levels are also available with our atom. So, in this configuration, in electronic configuration, we are going to write in A levels. Mainly, we are focusing on the sub-energy levels. We are focusing on the sub-energy levels and the number of electrons with them. In O levels, you had focus on the energy levels and the number of electrons with them, the 288. But in A levels, we are focusing on the sub-energy levels and number of electrons with them, right? So with that focus, we are going to write the electronic configurations in A level, right? That is the acceptable electronic configuration in science, right? Not the 288 thing nowadays. Nowadays, we accept the electronic configuration written in terms of sub-energy levels, right? So you know the sub-energy levels, right? One is the only sub-energy level available in the first shell, right? And with the second energy level, you are with 2s and 2p subshells, right? And the third energy level, you are with 3s, 3p, and 3d subshells, right? So identifying those subshells and the electrons with them, we are supposed to write the electronic configuration with this section, right, in A levels. That is how we are supposed to write the electronic configuration, right? Okay, see, let's come across the tude there. Maybe you won't receive that thing, and definitely tomorrow you will receive that, right? Let's go to the note, right? It says, right, like this, electronic configuration, it says, electrons are distributed among the various orbitals of an atom based on relative energies of orbitals and Pauli's exclusion principle, and this distribution is called the electronic configuration. Yes, we had gone through that, right? Electrons are distributed actually according to Pauli's exclusion principle as well, and the Hund's rule as well, right? So according to those rules, not violating those rules, electrons are distributed in an atom, right? So basically, with the electronic configuration also, we are going to refer to those, right? So Aufbau principle. The Aufbau principle is the major principle. Actually, that is what we have used when filling the electrons. Actually, when we our earlier explanation, our earlier discussion, when filling the electrons to chlorine atom, we had started with the lowest subshell. We had started with 1s, and then we further fill the electrons then to the 2s to 2p, like that, right? So we have started with the bottom, with the lowest energy subshell. Afterwards, we fill the electrons to subshells with increasing energy, right? That is what we have followed. Actually, that thing which we have followed is referred to as the Aufbau principle, right? The Aufbau principle. Aufbau principle is when you are filling electrons to subshells, when you are filling electrons to subshells, right? No, sorry, when you are filling electrons to the atom, filling electrons to subshell is all about the Hund's rule. Filling electrons to one single orbital is all about the Pauli's exclusion principle. But filling electrons to whole the atom, filling electrons to all the atom, whole the atom, total atom is all about the Aufbau principle. Filling electrons to whole the atom is all about the Aufbau principle, right? So now we are going to discuss about that thing. So basically it says when filling electrons to the whole atom, you have to start with the lowest energy subshell, and then you have to continue, right, with the high energy subshells, right, like that. So you have to start with the lowest energy subshell, then to the next lowest energy, like that. You have to fill the electrons to the total atom, right? That is what the Aufbau principle says. Let's go to that. It says the filling of electrons in an atom begins with the subshell with the lowest energy. See, last time when filling electrons with chlorine, we had done that. We started with the 1s. We are not filled the electron, any first electron to the 2s, 2p, or 3s, or 3p. We just started filling the electrons with the 1s subshell. So the Aufbau principle says that the filling of electrons in an atom begins with the subshell with lowest energy, and continues upwards according to the Aufbau principle. Right? The Aufbau principle means it is came from the German word, the building up. Right? Aufbau means it came from the actually German word building up. Right? So let's see how the subshells, the energy of subshells varies according to this theory. Right? Okay. So to come up with the Aufbau principle, we have this kind of diagram. Actually, no need to memorize this diagram, right? So this is kind of a simple diagram to represent the Aufbau principle, right? So in the first energy level, you have only S subshell. In the second energy level, you have S subshells and P subshells. subshell. At the third energy level, you have S subshell, P subshell, and the D subshell. At the fourth energy level, you have S, P, D, as well as F subshells. At the fifth energy level, you have S, P, D, and F. You don't have any other, no need, right? We had discussed last day, right? No need of any other subshells, right? Up to the, as we know, only up to the 120 elements, right? So the sixth energy level, you could have like this, right? You may have 6F as well, but that is no need to fill up to the 120th element, right? So with the seventh, you will have this, right? This is how it looks like, right? So anyway, these things will be enough to come up with the 120 elements. But for our purpose, actually in A levels, right, we are referring to only up to the 54th element level. In A levels, the electronic configurations are expected to written only up to the 54th element. So up to the 54th element, the 6S is enough. 6S is enough. Let's see what will happen, right? So so what is the energy increasing order of the subshells, right? Let's come up with the energy increasing order. This is very, very needed to fill the electrons to an atom, right? Energy increasing order. With subshells. Let's see. So this diagram says like this. So you can start with kind of this. One is energy increasing order. One is, then 2s, then 2p and 3s, 2p and 3s, energy increasing order, right, of the subshells. Then 3p, 4s, 3p, 4s, then 3d, 4p, 5s, 3d, 4p, 5s, then 4d, 5p, 6s, 4d, 5p. Actually 6s is not needed. When we are referring to 54 elements, 6s is not needed. So these are the subshells with the increasing order of energy, right? So with the use of these subshells until the 5p, we can write up to the 54th element. The electron configurations of elements up to the 54th we can write with the use of these subshells, right? So that is all what we need to know when writing the electron configuration using this Aufbau principle, right? So first you need to know the energy increasing order of the subshells, right? So let's see what these things says, right? So it's like this, Chris, right? So let's think of writing electron configurations using this subshells. It's like this. So before writing the electronic configurations using this notation, right? These notations, let's think of the maximum electrons available with these subshells, right? So with the 1s subshell, the maximum electrons available is 2. Maximum electrons available is 2, right? With the 1s subshell, maximum electrons available is 2. With the 2s subshell, the maximum electrons available is 2 again. S subshell means this is this, no? S subshells, P subshells, D subshells. S subshell is with only 1 orbital. P subshell is with 3 orbitals. D subshell is with 5 orbitals. So the maximum electrons available is 2 with this one. With this one, the maximum electrons available is 6. With D subshells, the maximum electrons available 5 orbitals means 10 electrons. Right? This knowledge is important. So with P 2P, you have 6 electrons as maximum, 2 electrons like that. You can think of this now. 10 electrons, here 6 electrons, 2 electrons, 10 electrons and 6 electrons, right? So I'll simplify this configuration. This is where the second electron appears. With this 10 is done, I'll just write in the Nobel gas configurations list, right? I'll just write in the Nobel gas configurations. 2, 10, 18, right? Yes, Nobel gas configurations. Then here, up to here, 20 electrons are filled. 20 electrons are filled. At this point, 30 electrons are filled. 20 plus 10, 30. When filling the complete in the 4p, 36 electrons are filled. When complete in the 5s, 38 electrons are filled. When complete in the 4d, 48 electrons are filled. And when complete in the 5p, 54 electrons are filled. So up to the 54th atom, we are expected to come up with the configuration. Right. Okay.
In the SPDF, 2, 6, 10, 14, right? F orbital.
F orbital 14. F orbital 14. Right. But we are not supposed to use the F orbitals, right, when writing electron configurations up to the 54th. Up to the 54th, right, the F is not used. Right. So in our A levels, we are supposed to come up with up to the 54th element. Configurations are expected to written up to the 54th element. So no need of using F subshells when writing the electron configurations. But for your knowledge, yes, F orbitals are with 7. If subshells are with 7 orbitals, if subshells are with 7 orbitals, that means in kind of F subshell, you can come up to 14 electrons, right? Okay.
That total 32 is what's the total, sir? 2, 6, 10, 14, 32 total. The whatever we have done, 2, 8.
Yeah, 32 comes like this. So here, point is this. This is the first energy level now. With the first energy level, you have only S subshell now, only 2 electrons. With the second energy level, you can have 2 and 6 here now, altogether 8. Here 2. With the third energy level, it is 2, 6, actually 10 here. That is why 18. With the fourth energy level, if you fill all the subshells, 2, 6, 10 and 14 there. So that is why we say 32. Right?
We are going more than that, no? A level we are going more than that, no? So whatever we stop with that, no? A O level, no?
Yeah. Actually in A levels also the maximum electrons available with the main energy level is 32, because we don't have any other subshell no, beyond the F. Beyond the F, we don't have any other subshell available no. So that still we stop at 32. Right? Because for 120 elements, only 4 subshells are enough. Right? So that even in A levels, maximum number of electrons can occupy in a energy level is actually 32. Right now? Right. Okay. So this is actually our electronic configuration stuff. Right? This is actually our energy increasing order of the subshells, let's learn how to use this energy increasing order to write an electronic configuration for a given atom. Right. I'll do some examples. I'll copy some examples. Right. So this is what we need to learn. This is what we need to know. Not this diagram. Not this diagram. This is not needed. Right. So you should, but you should in your memory you should have this order in your mind. In your mind you should have this order. That is not a hard stuff to keep it in mind. Let's do some examples. Let's do some exercise, right? Exercises. Then ultimately you will find this thing in your mind, right? Okay, let's do something. Write some examples of writing the electronic configurations, right? Let's write. Let's copy some electronic configurations, some atoms, right? It is like this. I'll write some electronic configurations for few atoms, right? Then you get the knowledge of writing the electronic configurations, right? So let's think of the first atom. The first atom, our atom, first atom, the hydrogen, right? Writing the electronic configuration of hydrogen. See, hydrogen atom is with only one electron. Is with only one electron. So that electron should reside. That electron should occupy the 1s orbital. So as the 1s subshell, you have with only one electron. So that is how we denote that thing. At the 1s subshell, you have with one electron. So 1s1. That is the electronic configuration of hydrogen. In your O levels. Sorry? Yeah, power. Yeah. As the power, you denote the number of electrons. Number of electrons with the subshell. Right now? Right. Let's come up with another one. The helium. So it is again 1s appearing first. You can have 2 electrons, up to 2 electrons in S subshell. So 1s2. Right? Let's come up with next one. Lithium, the third atom. So with the 1s subshell, you can have maximum up to 2 electrons, right? Then we need 3 electrons in your atom, so that we have to come up with the next subshell. Next subshell is 2s. So there you can put the remaining electron. Let's come up with the beryllium, fourth atom. So you need to have 4 electrons there. So with the first subshell, you can have 2 electrons. With the second subshell, which is the 2s, there also you can have maximum up to 2 electrons. So beryllium concentration is going to be 1s2, 2s2. What about the boron, the fifth atom? Boron. You should have 5 electrons there. So the first subshell is 1s. It can occupy a maximum up to 2 electrons. The next subshell is 2s. That can occupy maximum up to 2 electrons. 1s2, 2s2. Still you are to put another 1 electron to fill the atom, right? So 5 electrons are needed. So you have to come up with the next subshell. So you can't put the 2s3 here, right? So the second subshell, S subshells can have maximum of 2 electrons. So that you have to come up with the next subshell to put the third electron. Next subshell is 2p. You can write the remaining electron there, right? That is borons. So like that, you can come up with the electron configurations, right? With the carbon, another example, 6. It is 1s2, 2s2, 2p. You can go up to 10. You can go up to 6 electrons at the 2p, but you need only 2 electrons to complete the 6. So just put that 2 here. 1s2, 2s2, 2p2. Right? That is how we are supposed to come up with the electronic configuration for these atoms using the cloud model, modern atomic theory. Basically here we are identifying the subshell with those electrons, identify the subshell with the number of electrons in it, right? So like that. So in your quiz, when you receive that thing, just go through that. In your tute, some spaces are given. Some spaces are given to write the electronic configurations up to the 54th element. To write the electronic configurations up to the 54th element. some spaces are given. So as a homework, just do that. You are supposed to write the electron coefficient up to this 54th element. Right. So I'll do some more electron configurations. Right. When you restitute, you can complete that thing. Probably tomorrow you will receive. Right. If you haven't got it yet. Right. Right. So let's write a few more. Let's try to come up with some more stuff. Right. I'll write the configuration for. Let's come up with the phosphorus 15th. I'll do some few more. 20th element calcium, and I'll do for 23rd element vanadium. I'll write for 27th cobalt, some 30 zinc. I'll write the configurations of these guys. See how these things will appear. Writing electron configuration is very important part, right? Writing electron configuration is very important section in A-levels, right? So let's write the stuff, right? So phosphorus, 15 electrons should be written. Let's write. Start. 1s can occupy only up to 2 electrons. Then comes the second subshell, 2s2. Then the next subshell, 2p, it can occupy up to 6 electrons. P subshell 6 electrons. So 10 done. Then comes the 3s. It can occupy only up to 2 electrons, 12 done. And then comes the 3p. It can occupy up to 6 electrons. So, but we need only 3 electrons, right? So 12 done, we need only 15. That means 3 will be enough. So you can put that 3 here. So that is the configuration of phosphorus. Let's copy the calcium. 20 needed. 1s2, 2s2, 2p6, 10 done. 3s2, 3p6, 18 done. 18 done. Then 4s2, 20 done. This is very important to mention here with the calcium. It is very important to mention, right? After the 3p, you go to the 4s, right? After the 3p, you are not supposed to go to the 3d. It is a special situation, right? Right? It's a VIP case. So after the 3p, right, the 4s subshell comes rather than going for the 3d. See? After the 3p, right? After the 3p, you come up with the 4s, not the 3d. With the first energy level, you are with only s subshells. With the second energy level, you are with s and p subshells. With the third energy level, you are with spd subshells. But after filling the p subshell, you fill the next 2 electrons to s subshell and then comes to the t subshell. So no need to completely fill the third energy level before going to the fourth energy level, according to the Aufbau theory. The Aufbau principle? Yeah. Sorry? Yes. So yes, but actually that is kind of a strong idea, right? So basically it comes from the quantum mechanics, right? So I'll give you a simple explanation. It is just a simple explanation, but the idea is rather than that, right? But I'll give you some little kind of explanation to grab the idea for you. But it is also always kind of mathematical stuff, right? Anyway, the point is this: that simply, I'm trying to explain simply, right? So some strong idea, right? But the case was this case, right? So just at the first energy level, right? The 1s is there. At the second energy level, the things are 2s and 2p are there, right? And the third energy level, right? So basically, the things are coming closer to each other. The energy levels are coming closer to each other, right? So gap here is greater. gap between these two are smaller, right? So you have 3s, the energy levels are coming closer to each other, no? Right? And 3p, right? And 3d, yes, kind of 3d is there, right? And the thing is, right, the 4s guys also are there. Actually, with the 3D, the 4s is very, very close to like this, very, very close like this. The 4s and the 4p and the 4d kind of 6, right? Okay. That is how energy levels are appearing. And even with the, when it comes to 5, right, 4s and 5s also is here, right? So such kind of a thing is there with the energy levels. So basically, I'll tell you something to memorize, right? So it is easy to understand, right? Before coming to the D subshell, right? The S of the next energy level comes. Before coming to the 3D, S of the next energy level 4 comes. Before coming to the 4D, S of the next energy level 5s comes, right? Such kind of a thing is there, right? That is actually the energy level diagram, right? That is how the energies are appearing before filling the electrons, right? So it is kind of a mathematical idea coming from the quantum mechanics, right? Some wave functions and the stuff, right? So that is why the thing, actually these things are very close to each other, very negligible space there between the two shells, right? So such kind of appearance is there with the energy levels. That is why the 4s comes. Sorry? Spectrum. Yeah. Yes, Chris, because in hydrogen spectrum, we are not referring to the subshells. In hydrogen spectrum, we are not referring to subshells. In hydrogen spectrum, we just refer to the energy levels, no? 1, n equals 1, n equals 2, n equals 3. That actually this thing counts with the Bose-Sommerfeld theory. So, but in your A levels, you don't have the Bose-Sommerfeld theory, no? Right? So that is why you didn't came across these things, right? So that is not accepted in the A levels as well, right? Not that much, right? So, but you should know that 4s comes before the 3D. Simply, I am telling you, before the D subshell, before coming to the D subshell of any energy level, right? S subshell of the next energy level comes. Before coming to the D subshell of the energy level, S subshell of the next energy level comes. Even with this thing, no? Before coming to the 4D, S subshell of the next energy level, the 5s comes. That should keep it in mind. Rather than that, no worries, right? Basically, energy levels are filled, right? And then the electrons will be filled according to energy levels rather than this is the exception, right? The 4s, the S subshells comes before the Ds, right? That should be noted, right? So that is why very important when it comes to the element number 19 and 20. When it comes to element number 19 and 20, remember that don't write the 90th electron into the 3D subshell. The 19th electron as well as the 20th electron with the 4s subshell, right? Okay. What about the other stuff? Let's come up with the vanadium very quickly. Go through these ones. The simple stuff, right? So 23. So 1s2, 2s2, 2p6, 10 done. 3s2, 12, 3p6, 18 done. 4s2, 20 done. Then comes the 3d. So 3 electrons are remaining. 3d3. Right now? With the cobalt, 1s2, 2s2, 2p6, 10 done. 3s2, 3p6, 18 done. 4s2, 20 done. We need 27. The next subshell is 3d. And we need only 7 electrons. Up to 10 electrons we can fill to the 3d. But we need only 7. No? So that is easy, right? So zinc, 1s2, 2s2, 2p6, 10 done. 3s2, 3p6, 18 done. 4s2, 20 done. Then 3d, we need another 10 electrons. Yes, we can fill up to 10 electrons for the d subshells. So 3d 10. So like that, we can fill the electrons to atoms, right? So I'll write the 54th as well, the ultimate atom, to come up with the ultimate idea, right? I don't remember the name. Let's put the name as X, right? No worries, right? It is the 54th atom, right? They will give you the name, right? No worries, right? Anyway, 54th atom. Let's write the configuration for this one. 1s2, 2s2, 2p6, 10 done. Always calculate in your mind. 3s2, 3p6, 18 done. 4s2, 20 done. 3d10, 30 done. After 3d, right? Yes, this one, right? 4p6, 36 done. Before writing the 4d, you have to come up with 5s, right? Before writing the 4d, you have to come up with 5s. Before writing a d of an energy level, you have to come up with the s subshell of the next energy level, 5s. S can have up to 2, 38 done. Then you can write it 4d. You can have up to 10 there. 48 done. Here 36, 32, 8, 48. Then comes to the 5p. So that is actually how many electrons needed? 6 electrons, 54, no? 6 electrons are needed. So that is how we are supposed to come up with the 54th element, right? So in your tute, you have to complete up to the 54th. Just go through like this, so you can complete up to the 54th, right? So another little point to tell you, right, when writing the electron configurations. So before winding up, we have to say that as well. So this is the way of writing the electron configurations. Very easy, right? Not hard. Only thing you need to know is, yes, you need to know this order of increasing order in terms of energies for your subshells. Need to know that, right? Okay. So complete the stuff in your tute, right? Okay. Then I need to tell you another very important stuff before the before we winding up the session, right? It is this, right? Yes, this is the normal trend of writing the configurations, but then we are with 4 special configurations. We are with 4 special configurations. Right? With 4 special elements. We have 4 VIP cases, right? In our A levels, we are referring to only 4 VIP cases. 4 VIP cases. 4 special cases. Right? 4 special cases. I'll explain the reason as well why these 4 configurations are that much special. Right? Those comes with your element number 24 and 29, right? Let's say 24, I'll put as this 24, 42, then 29 and the 47, right? So special configurations: chromium, molybdenum, copper and silver. These four guys will carry some special configurations, right? So you should know about the 54 elements, and then you should specially study about these four guys, these four special cases, right? Let's discuss about these things. With the normal configuration, right, the chromium should appear like this, no? 1s2, 2s2, 2p6, 10 done. 3s2, 3p6, 18 done. 4s2, 3d4. With the normal configuration, it should appear like that. These also like this: 1s2, 2s2, 2p6, 3s2, 3p6, then 4s2, 3d10, 30 done. Then 4p6, 36 done. Then you have the 5s2, 38 done, right? Then you have the 4d4, right? This is about the molybdenum, but this is a normal way of writing. But remember, Chris, these guys are VIP cases. What makes these guys VIP? The thing is this: actually, the scientists have found that, right? Scientists have found that, right? There are few special configurations. Available like this. The point is this: they are found that these configurations means when your subshell is completely filled. That means if you are with a S subshell, when it is completely filled like this. If you are with a P subshell, when it is completely filled, when it is with 6 electrons. When you are dealing with a D subshell, when it is completely filled, means when you are with 10 electrons with the D subshell. Scientists have found that these configurations as well as these configurations, when the subshell is exactly halfly filled, P subshell can occupy up to 6 electrons, but when it occupies 3 electrons, exactly halfly filled. D subshell can occupy 10 electrons, when it occupies 5 electrons, exactly halfly filled. Scientists have observed that, right, when this configuration happens, when your subshell is completely filled or exactly halfly filled, right, when these things happen, right, they see that the atoms are very stable, atoms are very low with energy. So these are referred to as stable configurations. Right? When your subshells are exactly halfly filled or exactly completely filled, such configurations are referred to as stable configurations. So this thing is in your note, Chris. No need to copy this one. This is in your note. You can see that, right? So these are referred to as stable configurations. So that these guys, the chromium, molybdenum, silver and copper, those configurations can be stabilized if you are to release one electron from here to here. If you release one electron from here to here, then this configuration will be stabilized more, right? Stabilize more. Why is that? Because if you are referring to chromium's electronic configuration, right? This 3D4, this subshell is not stabilized, no? This subshell is not stabilized. But if you are to take this one as 4s1 3d5, 4s1 3d5, then you clearly see both the subshells are stabilized. Both the subshells are stabilized. So that means all the subshells in your atom, are now stabilized. If you are to put one electron from here to here, if one electron from chromium's 4s subshell is to put to the 3d subshell, then you will come up with 4s1 3d5. That means all the subshells are stabilized with this configuration. Because in here, only the 4s is stabilized, not this one. This is not a completely filled or exactly half filled situation. But with this confirmation, both are stabilized. Why? Both are coming under stable configurations. 1s1 is exactly half filled and 3d5 is also exactly half filled. So with this one, the chromium atom is more stabilized, so that chromium shows this configuration, the red colored configuration, rather than going for the black colored stuff. 1s2 2s2 2p6, 3s2 3p6, 4s1 and 3d5 is your electronic configuration when it comes to chromium. Those are the VIP cases. For the molybdenum, again the same thing. With these two guys, the 4d4 is not stabilized. But if you put one electron from here to here, that will make this configuration as 5s1 4d5, so that all the subshells in this thing is stabilized, even the ultimate subshell, right? 4d5, it is stabilized. So molybdenum prefer the red colored configuration rather than going for this stuff, right? So that is the molybdenum's case, right? So we have another two. These are referred to as S1 D5 configurations. S1 D5 configurations. S1 D5 configurations, right? So quickly complete this one, right? These are configurations as S1 D5 stable configurations. So we have another two. Right? Let's come up with the other two as well to wind up the session, right? So with the molybdenum and with the copper and silver. See, copper 29th and silver 47. Copper normal configuration looks like 1s2 2p6 10 done, 3s2 3p6 18 done, 4s2 3d9. That is what normally looks like. For silver, it is also 1s2 2s2 2p6 10 done, 3s2 3p6 18 done, 4s2 3d10 30 done, right? Then you will come up with 4p6 36 done, 5s2 38 done, and 4d 10 49 47 done. But when it comes to copper and silver, what happens is 3d9 is not such a stable configuration, but if you are to put this one to here, one electron from here to here, you will come up with 4s1 3d10, so that both the subshells are stable rather than only one subshell is stable here. So copper prefers this configuration rather than going for 4s2 3d9. Copper prefers the 4s1 3d10. In this case also, if you put one electron from here to here, you will come up with 5s1 and 4d9. So 4d10. One electron is put from here to here, so that this is more stable because all the subshells are stabilized now rather than going for this. So copper and silver prefers these kinds of S1 D10 configurations right, rather than going for the normal configuration pattern, right? So these are referred to as S1 D10 stable configurations, right? Those are the special 4 atoms we should know when it comes to A levels. Some few abnormal situations are there, but in A levels only these 4 abnormal situations will be handled, right? Will be concerned. So rather than these 4, you can come up with normal way of writing for elements up to 54th. Right, no? So you can quickly write these things, Chris, or I'll send you a picture. Considering that, do you have any other questions? Any question regarding this thing, Chris? Are you clear with this stuff? Right, no? Okay, if you have any questions, just feel free to send me a message as well. So I'll send this picture for you to complete the note. So as soon as you got the tute, just complete the stuff, right? You are supposed to write the electron configurations for all the 54 elements. When writing these 4 guys, right, just do this change. Those are VIP cases, right? Okay. So I will send you the picture here. Yes, next class we are going to learn about, first we will start with the configurations of the cations and the anions and the shorthand notation, that is very important as well. Then that will be basically 1 hour work of writing those things. Then we'll start writing the successive ionization trends, and I am hoping to come to the effective nuclear charge as well at the next class. Effective nuclear charge means it is kind of a periodic trend. That is the last section of the lesson. We'll start the effective nuclear charge as well at the next class. So those are the things we'll discuss at the next lesson. Right now. Okay, Chris. Then we'll stop with this one, right? You are not with any problems, no? Right. Okay, then if you have any, just feel free to put some message for me, right, with me. All right. So let's wind up at this. So good night.